So guys, welcome everyone to the second session of Rust programming. I would like to share an experience with you. Yesterday, I was actually watching a YouTube video by LGR. It stands for Let's Get Rusty. It's actually a YouTube channel in which a person who just shifted from JavaScript to Rust is discussing about the use cases of Rust and moreover what are the challenges that you can face while you learn Rust. So the issue that he put forward was the steep learning curve for Rust. Okay, and debugging is really crazy in Rust. So you might have gone through the first session, and we did get a head start of around 5 days. So I believe honestly that you guys have tried out some of the simple programs in Rust, like using loops and conditionals, printing statements, etc., etc. From today's session, we'll be discussing about the core features of Rust, which makes Rust unique from other languages. Okay, so Rust has got some of the different approaches that no other language has put forward till right now. And that is what we will be learning in today's session. And the point is to learn about ownership and references. For those who are actually in the coding space, you might have heard of what is a reference and what is pointer, etc., etc. For those who are new, this would be one of the best chance for you to learn what is reference and what are pointers, etc. So yeah, in today's session, we'll be talking about ownership. Now, when you hear the word ownership, the idea is to own something. Okay, so you might be owning a house, you might be owning a car, you might be owning your clothes, anything, right? So in Rust, this is actually a feature, and what it does is it provides us with memory safety. That means ownership is a unique feature that has deep implications in the Rust language. Now, what we use it is to basically to give the ownership of a particular value to a specific variable or a function block so that it only depends on it. Okay, so once you actually pass on the ownership from one person to the other, the old person is not an owner of the object. Similar to the case with you guys. Okay, if you actually sell something to a different person or another person, then you are now not an owner of the object, right? So that's the idea that we are trying to convey. Now, what is a garbage collector? If you are familiar with Python programming, then you might know that Python uses a garbage collector, which does automatic memory freeing and allocation for us. Okay. Now, it's actually an easy case to do, whereas in C++, you need to do it in manually by using the malloc and calloc function. Those who are actually like programming with C and C++ might have heard these keywords. Okay, so there are different approaches to take programming into consideration, memory management as an all. So we have garbage collectors, we have direct, what do you say, manual memory management. Okay, but then there is something in between, and that is what we have in Rust. It is called as a borrow checker. Okay, yeah. In memory management in C++, we must explicitly allocate and free the memory. We use malloc and calloc functions to allocate a required amount of memory, and then we pass it into the required variable. Okay. Now in Python, we have garbage collector which does this stuff for us. So we are not directly interacting with the memory. Whereas in Rust, it is done via ownership with a set of rules with compiler checks. First question is, out of the following, what kind of memory management is implemented by Rust? The first option is explicit allocation and free. Second one is garbage collector. Third one is ownership and borrow. And the fourth one is none of the above. The second question is state whether true or false. Ownership and borrow methodology is best for memory management on comparison with garbage collector and explicit allocation and free. Okay, guys, you're free to answer the question, and you'll be given around a minute to answer. So I want everyone to try the problems as soon as possible. You can see the answer. The first question, the answer was ownership and borrow. Out of the following, what kind of memory management is implemented by Rust? The second question, state whether true or false ownership and borrow methodology is the best memory management on comparison with garbage collector and explicit. Yeah, that's also true. It is a stack and heap. Okay. So people who actually know or have heard about stack, those who have learned about DSA or data structures for enthusiasts, or even for those who are learning C programming or Python, anything, you might have heard of stack. Stack is basically an LIFO data structure. Okay. LIFO means last in, first out. So what has been sent the last would be the first one to be accessed from a stack. Okay. Now you might have heard of stack, and you might, if you know threading or multi-threading, then you know that different threads are placed in different stacks. Okay. Now there are two operations possible with stack, that is the push and the pop. Push means to push into the stack or to insert an element into the stack, whereas pop means to take out an element from the stack. Okay. Now, data with unknown size at compile time or size that might change must be stored on the heap. Now, this is the case. Okay. So we have two different kinds of data types. Now, the one whose size is actually known at compile time. So the good examples are I32, F64, F32. We actually know, like, okay, this is going to be 32-bit. So we can allocate the required amount of space as we during the compile time. But this is not the case with string. This is not the case with struct and etc. because we might have some data structures which may be growing. For example, vector is a dynamic array which can grow. String can also grow when you can actually add or push stuff in the string. Okay. So in these kinds of data structure, we need to keep them in the heap instead rather than keeping them in the stack memory. Okay. So there are two different kinds of data types whose size is known at compile time, which is placed in stack, whose size is not known at compile time, is placed in heap. Okay, we talk about something called a copy trait. Now, copy trait is a particular kind of trait that we implement for those data structures whose size is actually not known at compile time. And these things or these structures, for them, the copy trait is not implemented. And for those whose size is known, like I32, F64, these things have its copy trait implemented already. So once the copy trait is implemented, that means we can move a variable's value to another variable, and this would be like creating copies. So when you just create a variable x and then you pass its value to y, then both x and y will contain the same value. Okay, so for those structures whose copy type is implemented, and those are those structures whose size is known at compile time. Okay, so these things like I32, F64, the copy trait is already implemented, but for string and other data structures, they are not implemented. The first question is, stack is a dash data structure. Okay, the options are LIFO, FIFO, array, hash map. The second question is, state whether true or false. Copy trait is implemented for string. The options are true and false. Yeah, so the first question was, stack is a dash data structure, and the answer is LIFO. State whether true or false, copy trait is implemented for string. The answer was false. That means copy trait is not implemented for string. That's what I was trying to convey. That copy trait is only implemented for those data structures whose size is known at compile time. Okay, we'll talk about ownership rules and scope of variable. Okay, so you might have heard of this word on a scope. So what is scope? Scope means the area or the definition or the area where its value is actually pertained. So when you create a wrapper, like the opening and closing brackets, and then you place let x equal to 25. Not yesterday, I think on the 11th, I've already shown you an example of shadowing. Shadowing is actually a part of the scope variable. Okay, basically what happens is when you create a wrapper and when you define a variable inside a wrapper, its scope only exists inside that wrapper, okay, or that block. Now, this particular kind of value cannot be accessed outside the scope. Okay, outside the scope means outside the block, you cannot access it. So when x comes into scope, it is valid, and it remains valid until it goes out of scope. Okay. Now, I want you to learn about the string data structure. String is basically a set of characters, or it is an array or a set of characters. String is basically any kind of word that you represent in an English language. So string type is stored in the heap because we may not know its size at the compile time. Okay. And how to create a string? This is how we create a string. That is, let x equal to string from hello world. So what happens is we create a string from hello world, and hello world by default is an and str, and what we are creating here is a string data type. So there are actually two string data types in Rust, but right now I want you to learn, okay, this is the string, and basically what happens is, um, here we have a string type. So we do have two different types, and the first one is the string, that is a large one that you can see, let x equal to the string, and then we have another string that is the and str. Okay, the and str is by default a literal, can be described as an and str. It is actually a pointer representing or pointing to a particular string. Okay, so these strings can be mutated, whereas the string literals can be as their pointers. Okay, so guys, I want you to pay as much attention as possible, because we are going to discuss some of the major topics in Rust. Okay, so first, I'm going to start a new program, and that should be begin with an fn main function. Okay, and then we are going to create a string. So let x, let's name it. Okay, let s equal to string from hello world. Okay, so now we have created a string with the content hello world. Okay, now if you want, you can print it using the println function, that the string is s. Okay, you can do it, but this is not the interesting part. I want you to show something interesting. So let new str is equal to s. Okay, now let new str is equal to s. So what I'm trying to do, I'm trying to pass the value of this s to the new str variable. Okay, and now I'm trying to print ln new str is new str and s is s. Okay, now let us compile and see what will happen. So Rust C ./practice.rs. This is how we compile a single Rust file. Okay, so when I compile, you can see an error. Now this is what I would like to show you, that you can see this way. I think this is visible, right? The terminal is visible. Okay, okay, then you can see that let s equal to string. Here it says that move occurs because s has the type string, which does not implement the copy trait, and I have moved my value of s to new str. So what happens is, I have moved the value in s to new str, and then I am trying to access s in the third println statement. Now this is invalid in Rust, because a type whose copy trait is not implemented, its value can be moved. But the problem is, once you move the value from an initial variable to a secondary variable, then you cannot access the initial variable. Okay, I think that is clear. So, but I want you to show something interesting again. So let's pay attention. Rather than the string whose copy trait is not implemented, what if we try with let x, which is I32, is 25 or like 35, and let y equal to x, and then I'm going to use my println function, that x is x and y is, yeah, so you don't want this. Okay, now let's compile. As you can see, there is no compilation error, I guess, so it takes some time to compile. Yeah, there is no compilation error. Now we can actually see the execution. ./practice.exe, and see that x is 35 and y is 35. So what happened? Now both x and y contain the value 35. But this is not the case with string, where the string passes its value to the successor when we do a move. Okay, I think that idea is clear. Now this is very important. So whenever you try programming with strings, keep this in your head that once you move a string from one variable to the other, you are not able to access it from the first. Okay. But what if we can still access it from the first? Okay. Now let's see that. So coming back to the old program, you see, I just tried to pass the S itself into the new str. Okay. Now what if I change this to s.clone? So what happens here is we take a clone or a copy of the S and we are passing the copy to the new str. Now this is where the idea of ownership comes into play. So previously we were trying to send the ownership of the hello world string from S to new str. But right now what we are trying to do is we're trying to take a clone of S and then we are sending this clone of S to new str so that the ownership of the hello world still remains with S. Okay, this is a bit hard to understand, but try to get it from the examples that is being shown right now. So the ownership of the hello world string remains with S even after passing it to new str because we took a clone of S. Okay, now these are stuff which are actually peculiar to only Rust. So try to understand. Okay, now let's compile again. So Rust now it compiles, So now it's yeah, string is hello world and new str is hello world and s is also hello world. Okay. So what happens? So new str and s both can be printed because we have only passed a clone of s to new str. Okay. Think the idea is clear. Now that was all for ownership. Okay. So the idea is to take a clone in order to pass it to a next string. Okay, now there is also one more thing that we need to discuss, that is to pass a string to a function. Now this is also one of the largest menace or bugs that you can see in case of Rust if you're trying to program with Rust in a long period of time using structs and all other different kinds of objects. See, once you pass a particular kind of object or a variable's content into a function, unless you don't return it back from the function, you cannot access it in the main function. Okay, some of you might have understood. Now I would show you an example. So I have created a string s, and I'm going to pass it to a function called display string. This is my own function. Okay, display string s. So I have passed the variable to display string. This is a function that I'm going to define right now. So in order to define a function, we need to use fn, the name of the function. The spelling should be right. Okay. And we are passing s, which is a string. And we are not going to return anything. Just we are going to print ln the input string is s. Okay. Yeah. Now let us execute this. No, there won't be any kind of, okay, I'll show you the execution. So when I execute this program, there is no error. And as you can see, when I execute, you can see the output. It prints the input string is hello world. Okay. Now it's because it is executing the function call. Okay. So it's executing the function call. That is when you call the function here, it executes the function body. And that is why we are seeing the println and the input string is s. I think the idea is clear. Now, what we will do is we would try to println the string in main function is s. And the string in my function is s. Okay. Now let us try to compile the program. Okay, now you have an error. Why? So if you see the error closely, now one of the habits that we need to create while programming with Rust is to understand the error messages, because Rust compiler gives some of the most beautiful or informative kind of error messages that can be used to solve the problem sometimes easily. Sometimes it won't really help you at all. It would put you into much kind of like harder levels. But mostly it is really useful and it's really appreciable to read it and find what is happening with the program. So if you see, first we have created the variable and we have passed its ownership to S. So now the ownership of hello world is sustained within S. And now I'm passing this S to the display string function. Okay, now what happens is when I call S in the display string function, what happens is this S is being taken by this function. Now the current owner of the S is the function display string. Okay, the function display string. So the ownership of S in the main function has lost its content and it is being passed to the display string function. So now after passing that, you cannot access that S here. Okay. So once it's similar to the previous case where I showed you, like let S is this and new str, then once I pass the value new str, then I cannot access the value from S. Now rather than passing it to a new variable, I'm passing it to a function. So once I pass an S to a function, then I cannot access that value. That means you cannot access this value S after you have passed it to this function because you are not returning the value back to here. Okay. Now the question is, how can you solve this problem again? So what if I just add an S dot clone? Okay, let's see what happens. Okay, now the program runs well. So yeah, it will be executed. Take some time in my system. I don't know why. Yeah, now you can see two print statements would occur because of the first one being the function call and the second one being the println that is being written in the hello, that in the main function. Okay, I think you got an idea. Now, I have just used clone like literally in everyone. And the question that would be arising in your mind would be, then why are you implementing such a feature if you can use a clone to solve this problem? Well, the idea behind using clone is actually use of clone is not advised because it's an expensive process to do so. We have one of the easiest process in order to solve this same problem using references. So memory allocation with strings, we have discussed in order to support a mutable global piece of text, we need to allocate an amount of memory on the heap unknown at compile time to hold the contents. I think this is clear with you because we need to store the string in heap as it might grow in the future. Now the memory must be requested from the memory allocator at runtime and we need a way to return this memory allocator when we are done with the string, and that first part is done by so when we call string from this implementation, this is how it actually works. So when you use the string from, you are actually taking the memory, asking the memory, and then you will return it once you actually pass it to some kind of function. Now the basic idea is when you pass a particular variable into a function and the function call has been completed, then a drop function will be automatically called in order to throw away the particular variable. Okay. So the memory that has been occupied by the variable would now be destroyed or now be freed so that it can be used for another variable declaration. Okay. The idea is so simple. Just keep this in mind. So for those who are actually not familiar with memory management and other computer science fundamentals, it might be a bit hard to understand. But please try to go up with me because in the programming side, it won't be much of an issue. But to understand, the concepts of the language, you might require to know what is memory allocation and all other stuff. Okay, like the different kinds of algorithms and best fit and all kind of, you might be knowing it. Some of you might not be knowing it. It's not very important for us. Okay. Now, that is it. Once returned, the variable will go out of its scope. And there is a natural point at which we can return the memory our string needs to the allocator when S goes out of scope. And and this function that it calls for us when it goes out of scope is called as the drop function. Okay. It's very important for you to know what is the drop function. And so Rust calls drop automatically when a particular string goes out of the scope. So after the function has been called and its call has been completed, then any variable that is present inside the function which is not returned back to the main function will be dropped. So the first question is, what function is called by Rust whenever a variable goes out of scope? The options are free, drop, deallocate, delete. The second question is, out of the following, which is immutable by default? And str, string, vec, array. Okay, it's time to close the boards. I'm going to share the results with you. So the first question was, what function is called by Rust whenever a variable goes out of scope? The answer is drop. And the second question is, out of the following, which is immutable by default? I have already mentioned that a string is mutable, but an and str is immutable by default. Okay, try to understand this time. An and str is actually a pointer to a string. So it is immutable by default, but a string is actually a more powerful data structure. So it has got a lot of options for it to be like what to be changed and mutated to add more or to append more or push something into the string, concatenate string, remove something from the string, etc., is possible with the string data type. Okay. Yeah. Now I wanted to talk about shallow copy and deep copy. So what is shallow copy? So the concept of copying the pointer, the length, the capacity without copying the data is called as a shallow copy. So in a shallow copy, we won't copy the data. Rather, what we would copy is the pointer to the data stored in memory, the length of the data structure, and the capacity that it can hold. Okay, these are the only things that will be copied. But Rust invalidates the first variable instead of being called as a shallow copy because it's known as a move. And Rust will never automatically create deep copy. Okay. So what is a deep copy? In deep copy, we will also take the entire data and then we will copy everything into the next variable. So when you use move, what happens is, see here, when you create an S1 and then you pass to S2, this will generate an error stating this cannot be accessed. And here, what happens is, when we try to pass the value of S1 to S2, we are actually only passing the stack contents of S1 to S2 and never copy the heap contents. Okay, so you're only copying the stack contents, and stack contents by means you are copying the pointer. So once you copy the pointer of the string hello from S1 and place it to S2, then the issue is S1 no longer has control over hello. It is always with the S2. Okay, and that is a shallow copy, and only Rust does shallow copy, does not do deep copy by default. Deep copy is being taken when we actually copy the data and then we pass it to the new. Now, deep copy is an example when I have used the clone function. Okay, when I use the clone function, you saw that there is no error in the compilation. Why? Because I'm taking a deep copy. By default, Rust does not take a shallow copy. That is, Rust will never automatically create deep copies of our data. Therefore, any automatic copying can be assumed to be inexpensive in terms of runtime performance. Yeah. So first question was, state whether true or false. Rust creates a deep copy of our data automatically. The second question is, automatic copying in Rust is expensive. That is also a straight true or false question. And both has got options true and false. Please feel free to answer the questions. So the first question was state whether true or false. Rust creates a deep copy of our data automatically. The answer was false. The next question is, automatic copying in Rust is inexpensive. The answer is true. Okay. So automatic copying in Rust is inexpensive because Rust only takes shallow copies. So with the clone, we have already discussed about the clone. So don't have to worry about it. So what did we do? We took a deep copy by using the clone function. Okay. So the idea was to use a clone function, not to take a deep copy. So we are actually copying the data along with the pointer, the data structure, the size, everything. And then we are passing it to S2. So now S2 is actually having a duplicate or a copy of the contents of hello, and these two things are independent of each other. So we are not actually taking the ownership of hello from S1 to S2. Rather, we create a copy or a clone of hello and then we will pass it to S2. Okay, now S1 and S2 are two independent variables. This works just fine and explicitly where the heap data gets copied. When we see a clone, we know that some arbitrary code is being executed and that code may be expensive. Now, why is the code expensive? Because you need to go to heap, you need to copy the data from heap, and then you need to pass it to the new variable. Okay. Now, copy trait. You've discussed about copy trait in the beginning of the session. That is, Rust has a special annotation called as a copy trait, where is we can place on type that needs to be stored on the stack, for example, like integers. And then if a type implements a copy trait, variables that use it do not move, but rather are trivially copied, making them still valid even after assignment to another variable. And as in a general rule, any group of simple scalar values can implement a copy, and nothing that requires allocation is of some force of reserve. That is, any scalar data type that we have discussed in the previous session, that is anything that holds a single value, it could be a character or a char, integer, float, etc., usually has its copy trait already implemented. Whereas data structures like string, whose size may vary during runtime, those things which are actually kept in heap, for them, copy trait is not implemented. Okay, I'm actually repeating the same sentence multiple times so that you can try remember that this is the case with scalar and non-scalar different kinds of data types. Okay, return values and scope. Yeah, so return values means, okay, we can also bring out the ownership by doing something like, if you see, you create a function here that is define read string, and you create a variable s that is hello world, and then you just create like s is equal to read string s. So what are you doing? You're actually passing that variable s to the function read string, and this read string, what it does, just returns back the variable to s again. So what happens is, now initially you have the variable s which holds the ownership of the hello world. Okay, now we pass it to a function called a read string. What read string does? Read string would return this s back. So now what happens is, s, you can see the next s in the second line, right? So the s will get back the ownership of what has been lost initially. Okay, now we are returning it back to s again. Okay, I think the idea is clear. So now s is in the main function, and now you can use it to print s. So what we are trying to do here is, rather than printing, I'll just do return s. Okay, return s, and what I will do is, s is equal to display string. Now what happens? So initially I created an s, I passed this s to this display function, and I'm returning it back. So what happens is, this s will contain the value of hello world. Okay. Now what happens is, the string in the main function is s. Now what happens when you try to compile and say return s found? Oh yeah, I haven't specified a data type of return. I think that should be the problem. This issue. First assignment to us, help consider making this, yeah, okay, mute, because I've changed its value, right? That is the issue. So we need to read the errors so that you can make it right. Now practice. Yeah, you can see the string in main function is hello world. So what happens? I passed it to a function, the function returned me that string. So I still have my s back after being returned, and then now I can access it in the main function. Okay, so that is the idea behind return value and scope. Now you guys need to try as much examples as possible with ownership, because this is a particular stuff that is really hard to understand, and so you need to try creating different kinds like arrays, vectors, and then vector is actually a dynamic data type, so it can grow during the runtime, whereas arrays are not. So what you can do is like create a vector and then push some elements and try to pass it to some other function and try to edit it. If it is set as mutable, then you can edit. But you can try these kinds of examples for yourself and see what happens when Rust gives some error. Okay, first question is, check whether the following statement is true or false. Ownership of a variable is passed to a function when we pass the variable into the function. There are two options, true and false. And the second question is, which is the trait that is implemented for types that are placed in the stack? The options are copy, debug, clone, and hash. Okay. share the results with you. The question was, ownership of a variable is passed to a function when we pass a variable to a function. The answer is true. The second question was, which is the trait that is implemented for types that are placed in the stack? And the answer is copy. So we will talk about references and borrowing. Okay, so what is a reference? So reference is basically a pointer. A pointer is basically an address. So what is the difference between data and pointer? So data means it contains the actual data of what you have. For example, for a string hello world is the data. Now, what is a pointer to this data? Pointer to this data means it is an address to the memory location where it is actually stored. Okay, it is an address to the memory location where the data is actually stored. Now, you can access the data in two ways. By actually having the data itself and by having the address in which it is stored. So, if you have the address, then you can go there and then take the contents, right? That is the idea. Okay, so that is a reference or a pointer that allows us to access a data that is stored at the address owned by some other variable. I'll show you that example so that it will be more clear. The previous problem, what happened? So if you just change this to println the string inside my function is s. Now what happens? I created a string s. I passed it to this. I don't want to reassign. Okay. So I passed it to this function and then I'm trying to access the string s. But this is not possible because the ownership has been passed to this particular function, right? So this was the issue or the compilation error that we had before. Now, how to solve this problem in a less expensive way? The first method is to create a reference of s and pass the reference of s to the display string. Now, what is happening in real time is you are not actually passing the entire contents of s to the function. Rather, you are passing the address to that string into the function. So the ownership of the string still remains in the memory location with the s, and you're just accessing it with the function by using the address. So you're actually going to that particular memory location and then you are accessing the data. So when you place an ampersand sign before a particular variable, that means the pointer to that variable. For those who are actually familiar with C programming or C++ programming, you might be really good or will be understanding what is an pointer. For those people who are actually programmed using Java or Python, you might not be knowing what is a pointer, but pointer is basically an address to a particular variable. And when you place an ampersand sign before a variable, it actually points to the address of the variable. Okay, so we are trying to access the memory location where s is stored. Let's try to compile this program this time. And what is the error? The error states string. Yeah. So the data type needs to be changed. Okay. So now we are not receiving a string, but rather we are receiving an pointer to string. Okay, now try to compile. Yeah, it works. Let's execute. So when I execute the program, what happens? So it prints twice time, right? So it is the similar result that we got while we use the clone, but clone is an expensive operation. Why? Because we are actually entirely copying the memory location, or sorry, the contents, and then we are going to pass it to a new variable. And an easier method would be to pass the reference rather than passing the value all by itself. Okay, I think the idea is clear. The idea is to just keep a reference, that is to place an ampersand. Now, the main thing that you need to be sure is when you pass an ampersand s, you are actually not passing the value of the string itself. You're passing the address to the same. So you need to change the function definition. You need to change it to the data type and string so that it accepts an and string and not the string. Okay, so there is something called as referencing. This is referencing. And there is something called as dereferencing. Dereferencing means to use a star in the place of ampersand. Now, what is dereferencing? So dereferencing means you are actually going to take the value at the particular location. Okay. This is reference. I think that is the idea of references. We have discussed about the clone function. We have also discussed about the passing it as, wait, this is ownership, right? We should take a look. Yeah. So, yeah. So what I've already shown you is an example of a normal pointer or a normal reference. Okay. Now, what if I can use it to change the string? So let mute s and display string and s. And then rather than printing this, I am going to change its value like, okay, s dot push str. This is to append a particular string. Hi everyone. Okay. And now let's see. Okay, there is an error. Oh yeah, now we need to change this data type to and mute string. Okay. So once you change this to this, now this is a data type. I want a mutable reference. So once I create a mutable reference, now this works really well. And when I execute, this is fun. Okay. So when I execute, you can see the string in the main function is hello world, hi everyone, right? So if I place a space here, it is more readable. Okay. So guys, what happens is I am going to create a string s and I'm going to place it as mutable so that I can change it in the future. First point. The second point is I am going to pass an and mute s. Now what is this and mute s? This means it is a mutable reference. That means the reference or the address can be used in order to change the value that is being holded by the variable. Okay. So you can use the pointer to actually change the value in the memory location. That is the idea of having a mutable reference. Now, when you come to the function, you need to change the data type to and mute string because you are passing an and mute string and not a string. And now what I did was s dot push str. Hi everyone. Now this push str is a function that is used to concatenate or to push or to append another string to the existing string. Okay. So that is the idea, to append a string to the existing string. Now you might have seen similar like functions in Python, extend and strcat in C, etc. So this is the similar function in Rust is to have a push str function. Okay. Now what happens when I execute, when I compile and when I execute, what happens is now I am going to try to access the s in my main function. But what happened is when I call this function, I've already changed its value to hi everyone has been pushed into the string so that my current s value will be hello world, hi everyone, right? That would be the step because I have already changed it in the memory. So the string value has been changed in direct memory by using a mutable reference. I think the idea is clear. Okay. So that is the stuff about mutable reference. That is something that we have discussed right now. Now, what if I can have, see, in this example, if you see, this is an immutable reference. That means this reference is not used to change the value of s. So simple reference, and s. And s is again used. So how many, you can have many number of and s. Why? Because these things cannot change the value of the variable. Okay. So these are immutable reference. So immutable reference cannot be used to change a value of a variable which is present in memory. But then I'm going to create an mutable reference after these things. So when I create a mutable reference R3 to this, the issue is now I have R1 and R2 pointing to what? See, I'll show this example so that it could be more easily clear. Okay. I'll just come to here and we don't want this. Okay, we have created two references. These are like immutable reference, and this one is actually a mutable reference. Okay, so now I create a mutable reference. Now let's see the execution. So we only have a warning because we have actually used, now see, I have created two different immutable reference and I have used it here, right? What if I just remove this use case? And now I create an immutable reference and then I'm going to print the value using the mutable reference, and then I'm going to print the values in the mutable reference. Okay. Now when I try to compile, you can see that it states this, this no problem, and this is on by default. So I think and just pass this to the upside, and then I'll try to access this one. Yeah, so now you can see the error. Okay, the idea is I have initially created a mutable reference, and now it says mutable borrow occurs here. So once you actually took a mutable borrow, that means a pointer who can actually change the value of the stuff in memory, and then you cannot have some immutable borrows. Now, why you cannot have some immutable borrow? Because when you have an immutable borrow, that means you are actually using this immutable borrow to see what is the value of the variable in memory. Whereas a mutable borrow is being used in order to change its value. Now, when you have a powerful tool like a mutable variable to change its value, meanwhile, you cannot have these immutable borrows, because this mutable reference can change its value in memory, and this R1 and R2, which is actually the immutable references, cannot actually see the change. Okay, so Rust will prevent this. Now, the idea can be shown in a simple XY diagram that I will show you. So X is a mutable reference that is pointing to a content A, and Y is an immutable reference that is pointing to the content A. Okay, so this is immutable and this is mutable. So now Y will contain A and X will also contain A. Now I am going to use this X to change A to A plus 1. Now what happens? Now what happens when I try to access B, access Y? So when I try to access Y, the issue is Y is actually pointing to A, right? But now we have changed the value of A. But this won't be like known by Y, because you have got an mutable reference initially. So once you have a mutable reference, then you need to use that mutable reference to make the change, and then only you are able to create immutable references to the same variable. Okay, these things could be really hard to understand because of the idea of referencing. First, this is actually memory management, different kinds of ways to access the memory. So once you have a mutable reference, you need to use it before creating any other reference. Okay, we have talked about reference. We have talked about borrowing. Borrowing is the same effect of referencing. Borrowing means to use reference to actually access the data from the memory. So ampersand represent the references. They allow you to refer to some value without taking the ownership of it. Okay, so we are not taking the ownership. We are just taking the reference, or we are borrowing. This is the method that I was explaining in the beginning of the session. That is, it uses a borrow checker. Now, because it does not own it, the value points will not depend or will not be dropped when the reference stops being used. So that is why there was no issue when we actually passed it to a function. Okay, mutable reference. We use the mutable reference to actually change. So mutable reference have one big restriction. If you have a mutable reference to a value, you can have no other references to that value until you have used the mutable reference completely. So the restriction is preventing multiple mutable reference to access the same data at the same time. Which, see, the issue is data race, or it can is multiple pointer can be used to edit the same data, which is possible in different languages like C and C++. You can actually take multiple references to a particular kind of data, and this is prevented using some other mechanisms like logs and semaphores. These are stuff that you might learn if you are a CS student and obviously been learning operating systems, compilers, etc. Then you might know about these things, about logs and semaphores, but it's not really relevant. The idea is to just keep in mind that once you have a mutable reference, then you need to use it before taking any other kind of reference. Okay. So the benefit of having this restriction is Rust can prevent data race at compile time. Okay. A data race is similar to the race condition that happens, and when two or more pointers try to access the same data at the same time. At least one of the pointers is being used to write the data, or there is no. So these are some things that you can actually consider. So we also cannot have a mutable reference while we have an immutable one to the same value. I'll launch the questions. The question number 1 is, which of the following symbol is used to describe a reference in Rust? The option 1 is an ampersand, then we have a star, then we have a percentage, and then we have a dollar sign. The second question is, state whether true or false we can have mutable reference while we have an immutable one to the same value. Option A, true. Option B is false. Take your time, think over what has been said, and answer wisely. I'm sharing the results with you. The first question was, which of the following symbol is used to describe a reference in Rust, and the answer was the ampersand symbol. The second question was, state whether true or false we can have a mutable reference while we have an immutable one to the same value. The answer is false. This is actually a tricky question. You need to think it again and again to make sure that you get the right answer. Okay, so what is a dangling pointer? Now, this is also again an operating system concept where we discussed what is a dangling pointer. So dangling pointer is a pointer that refers to a location in memory that may have been given to someone else by freeing some memory while preserving a pointer to that memory. So basically it is a pointer that used to point to a real-time data, but now the data has been cleared. Now the pointer is actually pointing to nothing. Okay, so that is a dangling reference. Now, this is usually a large problem in case of C programming or C++, and this is solved in Rust. So by contrast, the compiler guarantees that references will never be dangling, because if you have a reference to some data, the compiler will ensure that the data will not go out of scope before the reference of the data does. Okay. So dangling reference is basically a reference which is pointing to nothing. See, let me just create a pointer x which is pointing to the value y in memory. And now I have cleared the value y using a mutable reference. Now what happens? Now x is pointing to nothing, right? So this kind of a scenario won't happen in Rust, because Rust would obviously generate or raise a compile time error. But this is possible in case of programming languages like C, where you will be prompted by an error called a segmentation default core dumped. Okay, that is when it happens when you are having some dangling pointers, or you are pointing to a memory that has not been allocated, or you have not allocated memory, and then you're trying to access different variables, etc., etc. So there are different kinds of memory errors that usually happens when you are playing with pointers. Okay, so what is slice? See, a slice of cake or a slice of anything. So it's basically to have a subpart of something old, right? So something old, you can take a subpart. So slices are a reference of a contiguous sequence of elements in a collection rather than the whole of a collection. It is basically a substring or a subarray, something which is sub to our old stuff. Okay, so it's like when you have an array from 1 to 10, a slice would be an array from 2 to 4 or from 2 to 8. So it's actually a subpart of the entire stuff, right? And this is called as a slice. It's like the slice of cake. So you just cut the cake into different slices and you're taking a part out of the entire thing. Okay. Now sometimes we might need to access slices because we only want to take our concentration to that particular point. If you have did some problems like sliding window problems, then we are actually using slices or sliding window to pass from like the entire content of the the data structure. So it's what happens is in Rust, a slice is a kind of reference, so it does not have the ownership. Now, slice type reference is used when we have to return indexes of strings which are cleared without clearing the returned index. And here we would rather return the reference to the slice rather than an index. Now we have a straightforward API that is much harder to mess up. Okay, I'll show you some examples so that it will be more clear for you guys. Yeah, we'll come to slices. So this is array, like let mute data is 1, 2, 3, 4. And then I can create a mutable slice of the array that is let slice is and mute data. So what am I doing? I have created an array which is mutable. So this is a mutable array of I32, right? That is integers. So this thing can be changed. Okay, at any point of time, I can change its value. Now, what I'm going to do? I'm going to do is to create a slice, and a slice by means is a subarray. So subarray, now 1 to 4 means containing the elements from index 1 to index 3. So here it would be from 2, 3, 0, 1, 2, 3, 4, right? So it should be from 2 to 4. And the idea is you can also change, like this is, can change slice 0 equal to 10, slice 1 equal to 2, and slice 2 equal to 30. Now we are going to print the data by using the debug operator. Okay, now let's see what will happen when we actually try to change the data using this one. So yeah, so if you see that the first creation was 1, 2, 3, 4, 5, right? So the data was data, which is the array, was initially given the values 1, 2, 3, 4, 5. Then I created a reference to that array and named it as a slice. And this is a mutable reference, as you can see. So it can be used to change the values of this subarray. And now I am changing the values of the index 0th value of the slice to 10 and the index 1th value to 20 and the index 2th value to 30. Okay. And now I'm changing the values using the mutable reference. The slice is actually the mutable reference, not an array. It's a reference to the subarray. And now I'm going to try to print this initial array. So when I print that output, you can see the output came out to be 10, 20, 34, 34 and 5. Now why did it change like that? Because I changed the initial value to 10, I changed the second value to 20, and I changed the third method. What will happen if I would try to change slice 3 to 100? And then I try to compile, it still works. And then I do slices. Now you can see that the fourth value has been changed to 100. The fourth value is the index 3 value. Okay. So that is what we did using a slice. I think the idea is clear. Slice is basically a subarray. So slice type is a reference. So we do not, we can return index of strings which are cleared without clearing the return. Here what we do is we create a string, then we keep an ampersand s and we clear it. Now the problem is you have an ampersand s, that is you have a reference to the string which has been already now clear. Now the issue with this kind of a program is it would create a dangling pointer that I have mentioned before. So this would end up in an error because you are actually creating and passing a particular kind of ampersand s to the word, and now you are going to clear it. Okay, now what this first word function does is it will give you the index of the first word. Whereas in case of hello world, so this first word function is a it is not a library function. It is something that we have actually created by ourselves. Okay, so if you see in the back, you can see the first word function is actually taking the string and it gives the index to the value. Okay, so we keep the index to the number. What happens here is we will get the index value here, but the issue is we have already cleared the string, so we'll get a integer value to for the value word, but this s has been cleared. So the length is associated with the string. The length associated with the string has been already cleared. So now this will also bring a compile time error asking for resolution. This is not the case in any other language. If you see in C, it does allow you to do all these things and have all these kind of memory errors. Okay. So what happens is the let word will contain the index of the first word. And then we clear the string. Now what happens initially, you see, word actually has the size or the index of the first word, right? And we clear the entire string. Now what has it got? Like word has the index of the first like word in the string, but the word has been entirely cleared. Now what is it pointing to? It's like it does not have a relevant index because we have already cleared the existing string. So this would also be considered as a compile time error in case of Rust. This is really great because Rust can find these kinds of memory errors by default and will obviously show this at compile time, which is really great because we do not have to face this during the execution. The question is, which of the following is a slice equivalent to the entire string in Rust? Here X is the string. So the option A, which is S equal to ampersand X 0 to 2 and S equal to ampersand X, S equal to ampersand X 1, S equal to ampersand X 0 to X dot line. And then you have the second question, which is state whether true or false slice has ownership over the contents it holds. So the first question was, which of the following is a slice equivalent to the entire string in Rust? Here X is the string. So the answer is option B, that is and ampersand X 2 against everything. Okay. So it's a similar implementation that you can see in the case of Python also. When you can use this double dots or colons, in order to represent the entire string. And the next one is state whether true or false slice has ownership over the content it holds. So the answer is false. As I have mentioned before, does not have ownership. It is actually a reference. Okay. So reference, don't mess it up with ownership. Reference means you are actually only taking the address and not the value. Ownership means you're taking the entire value. Okay. And with that, we will go to the Q&A. Oh yeah, that we can have a mutable reference while we can have an immutable one, right? See, we can have a mutable reference while we have an immutable one to the same value. That means you can have a mutable reference to something while you have an immutable on to something. It is not possible. I have already mentioned to you guys that if X is an immutable value and it can only read from the memory, now you have a mutable reference at the same time. So when you have a mutable reference, it allows you to change the value of the particular variable in memory, right? But what is the case? Like if you have an immutable variable, then it is actually looking into that particular variable to get its value. While you use another reference, a mutable reference, to change its value. Now this change will not be seen in the case of an immutable reference. Okay. So that would obviously lead to something like a change that has been brought, but it is never noticed. Now, these kinds of errors are like relevantly seen in database. But if you see, serialization is important. The idea is whenever you have a pointer that is actually looking into a particular value, you cannot use another value to change its value, so that the initial immutable reference that is actually looking into it will have an error value by default, because it is looking into 3 and you used a mutable reference initially to change its value to 4. Now, by default, the pointer will not get the updated value.